Hi, this is Patel, and in this lecture we are going to look at the bars of uniformly varying sections. So this is different from the previous lecture. As you can see, here we have added bars of uniformly varying section. In the previous lecture we have seen the bars of the varying sections. So you will get the examples of the stepped bar or the bar which is changing its cross section. But in this particular bar, you will see that the cross section area of the bar is continuously changing or uniformly changing. So this is different type of the case in which you will get another equation to solve this type of example. So first of all, we are going to start our lecture with the theory of this particular type of the bar. As you can see, basic diagram of that particular theory is on your screen. In this particular theory, you will find that the bar is made up of the cross section which is changing continuously throughout the length. On this particular end, you will see that the diameter is D1, which is the bigger diameter, and on the other end, the diameter is D2, which is the smaller diameter. So now, if you see that the diameter is continuously reducing, that's why we have taken one strip or elemental area which is represented by this hatched line at XX section. This XX section is at the X distance from the diameter 1, or we can say that the left hand end. This XX section is of the dx length. The length of this section is dx. So which is very small length. You can neglect it as compared to the total length of the bar, which is nothing but the L. Now if you consider the force which is applied on the bar, which is nothing but the P force, it is of the tensile nature. We are going to calculate how much deformation will it cause into this particular bar. So consider this elemental section only. Diameter of the bar at the distance x from the left hand side. Let's say the diameter is dx. So we need to calculate how this dx can be calculated. So for calculation of the dx, we are going to look at this. This equation gives you the idea how to calculate the dx. So if you subtract these values from the d1, you will get the answer of the dx. How? For that, you need to use some geometrical methods, and for that we are going to draw a parallel line like this. So if you draw the parallel line, this entire length is of diameter d1. So if you want to find out the diameter of this length, you need to subtract this much distance from both the end from the diameter d1. If you can subtract it, then you will be able to solve it. Otherwise not. So we have done the same thing over here. We have done that through the length L, the diameter is reduced from d1 to d2. So for the length x, how much diameter will be reduced? So we have put some trigonometry relation, and through that relation we have maintained this equation. So if you subtract this particular part from the d1, you will get the diameter at the x distance, which is nothing but the d1 minus kx, where k is d1 minus d2 upon L. So this is how we calculated the dx value at x distance. Now if you look at the cross section area of the bar at this particular section, we need to calculate the area ax. In order to calculate the area, we need diameter, and which is calculated over here, as you can see in your screen. So d1 minus kx square into pi by 4 is going to give us the area of this particular section. If you put the value of area into this equation, that is nothing but the basic equation of the stress, that is force upon area, then you will be able to calculate, simplify this equation up to this point, which we have done by taking the 4 in the denominator, which will give you the answer as a 4p upon pi into d1 minus kx square. Now we are going to calculate the stress. How can we calculate the stress? Using the basic relation from the Hooke's law. What is Hooke's law? Hooke's law is sigma equals to E epsilon into E. We have made a subject epsilon and we got this equation like stress upon E. If you put the value of stress, then you will get the value of strain like this. Now we have stress and strain. We need elongation. In order to get the elongation, we are going to use the basic formula of elongation, that is nothing but the change in length upon original length. So epsilon x into dx is going to give us the elongation. So delta x is our intention to find out. So if you put the value of strain into this equation, then you will see that 4p into dx upon pi into d1 square, d1 minus kx square. Now let's go further. The total elongation of the bar may be found out by integrating this particular area. Now we have taken only one elemental area. We need to find out the integration for the entire length. As you can see, the length of the elemental area is dx. That's why we have used integration limits from 0 to L. So you can see the same equation of the x length elemental area with the integration limit of 0 to L. If we take out the constants 4p upon pi e from the integration, then the only thing which is remaining in the integration is 1 upon d1 minus kx square. Now if you integrate it, then using the integration, you can see that this can be taken in the denominator using the minus 2 sign, using the minus 2 power. Now if you do the integration using the basic formula of trigonometry, then you will get this particular equation. In this equation, we need to apply the limits from 0 to L. If you apply the limit instead of the x, then you will get the final answer like this. In this particular answer, we have inserted instead of x, one time L and another time 0. After simplification, you will see that k value is nothing but the d1 minus d2 upon L. So we need to put this k value into this equation. Due to this application, you will see that L gets cancelled out into this equation. So the equation remains into d1 minus d1 plus d2, and which will cancel out these two terms also, and only plus d2 will remain into this equation. So if you take LCM, then you will get d1 minus d2 upon d1 into d2. d1 minus d2 also gets cancelled from numerator and denominator like this, which will leave only this equation for us as the final equation of delta L of uniformly varying section. So whenever the uniformly varying section is asked in your examples, you need to use this equation to calculate the answer. Answer should be in mm because this is nothing but the change in length. So unit of this answer must be in mm. Now we are going to look at the practically example so that you guys can relate to these examples. So we are going to use one basic example. The given data is on your screen. Let's read out this data. The data says that find the change in length. Change in length means delta L of the bar ABC if it is subjected to gradually applied load as shown in a figure. So here we provide the figure. In this figure you can see that the AB part is uniformly not varying section, but BC part is varying section, where you can see there are two different diameters. Here at B diameter, let's say D1, and at C diameter is different. So we need to calculate the change in length using the formula which we have derived just in the previous slide. Now if you look at the portion AB, it is 10 mm in diameter, which is given in the given data. Portion BC is tapered section, but we know that AB section has a 10 mm diameter, so this diameter is known as a 10 mm. Now we need another diameter at this point, which must be given in the given data. The diameter at the C is 20 mm. As we have seen that the diameter at this point is 20 mm. The length of the portion AB is 1 meter and the length of the portion BC is 2 meter, which is also given in the figure. You can take that data from the figure also. Take the modulus of elasticity as 200 kilonewton per mm square, which is given, which means that the entire bar is made up of the same material. There is no mixture of the material. Now for the part AB, we are going to calculate the cross section area. Cross section area for the part AB is nothing but the pi by 4 d square, and the d for the AB part is given as 10 mm. So if you put that value in this equation, you will get the answer as the 78.53 mm square. Now we need a delta L, total delta L of the length. So total delta L is nothing but the summation of the delta L of AB and delta L of BC, which is the algebraic summation. So for that, we are going to apply the basic equation of AB, which is nothing but the PL upon AE, and basic equation of varying section, which we have derived in the previous slide. That is 4PL upon pi E d1 into d2. We have each and every parameters, like P is nothing but the 20 into 10 raised to 3. L for the first part is 1 meter. We have converted into the mm for that 1000 mm. Area is calculated and E is also given. Similarly, we can use that particular data in this equation for the part BC. For the part BC, the length is 2 meter. That's why we have written over here 2000 mm. Area is not given, but we need only D1 and D2. We need only D1 and D2. That's why we have entered 10 and 20 like this. The E value for both the part is the same. If you calculate both the values, then you will get the final answer of delta L as a 2.54 mm, which is increase in the length because the sign is positive. If you get the negative sign, which indicates that it is the decrease in the length. So for this particular example, we are getting the increase in a length, and which can be validated because the given force is of tensile nature. So this is how we are going to calculate our examples of the varying section, example of uniformly varying section. So we conclude our lecture over here, and we will see some few more concepts in the upcoming lecture. Thank you.